recorded. Okay, moving on. So let's check out our data here. So I sketched my graph here, units sold versus time. So describe the form of the distribution. What do you think? Now, R value aside for just a second, does this look like a line?
Somewhat.
Does it look more like something else?
Yes.
Yeah.
What does it look more like?
Exponential.
Okay, so in this case, what we're going to say is not what does it look like, it's what doesn't it look like. We are concerned with whether data is linear or not. So, what are we going to say about this? Describe the form. This data appears to be nonlinear. Is it exponential? Maybe. Is it logarithmic? Maybe. But at the very least, this statement is true because this is what we're concerned about. Check this out. We are comparing this to least squared regression line. We're concerned, is it linear or not? Okay? And so, when we find the least squared regression line, I'm going to scroll up a little bit. I'm a little bummed here. Because now my graph is all in the middle of my, I should have sketched off the sides. Check this out. So the form was nonlinear, and here's the problem, right? So I just said the data was nonlinear, and now I'm going to ask you a bunch of questions about what's the least squared regression line. How good is it? So do you think these two things are going to match up?
No.
Okay. How good of a car is a skateboard? It's got wheels. You can ride on it. Does it make it a good car? No. So I'm about to use a least squared regression line to describe data I just said wasn't really linear. Okay, so why do this? Just check out what we're getting at right now. Okay, so what did you find for the least squared regression line? Somebody read me what you got for your answer.
R equals a full answer. Y hat. 1.605x.
Isn't it the other way around?
A plus
bx.
Okay, so hold on. So let's start here. What should our form be? Remind yourself. It should be y hat equals a plus bx. What is y hat?
The predicted value.
The predicted value, in this case, the predicted number of iPhones. A is
That's where it starts.
the intercept, and what does the intercept represent in a least squared regression line?
Value
Value of 0, so at year 0. And then B is,
slope.
which is,
Yeah.
you must know this. You must know that. I'm telling you, you need to know these things. Okay? So your answer to this statement should start something like this. Y hat equals,
It doesn't matter if you put bx first or a.
let's use this form.
Okay.
Y hat equals what?
It depends if you used year like 2000 or years since 2000.
Okay? So what'd you use?
I put
I put the
then I graph years since 2000.
We should use years. Could it work the other way? Yes. Let's use the one that's years. Who used years? Okay, so what's your equation?
negative 3,222.6 plus 1.605.
Okay, that's not really actually good enough because I want to make a little context around this. Or what does y hat represent?
Units sold in millions.
So units sold hat equals negative 3222.6 plus 1.605, and what goes in my parentheses? Year. Why is this right here a good step to go through? It gives you context. It helps you know when you get down the line, right? We're about to start calculating residuals, which, by the way, what is a residual?
Distance between predicted point and actual point.
Yeah, difference between an actual point and predicted point. So think about Apple right now. in the course of this. So what they want to do is they want to say, in the year 2020, how many iPhones am I expected to sell? Do you think that would be really good data to know, to be able to predict? You do? Okay, so it's predicted, so this is a good equation to have, because if I can have a really good prediction, I can say, hey, we're anticipating to sell this much, then they can figure out a lot of different things about their company, right? What's our profit margin going to be? Not to get into economics, but here we go, right? So use the least square regression line to calculate the residual for 2007. What does that look like? Well, units sold equals negative 3222.6 plus 1.605 times 2007. And in this case, we're calculating the residual for 2007. Why is this a meaningful comparison to make? Like, put it in this equation and then compare it to something.
Because you see how accurate
You can see how accurate the line is. We know the data for 2007, right? We know that it was 0.5 units sold. Okay? So, what were they predicted to sell in 2007?
0.5. We know, negative 1.5.
Uh-oh. Negative 1.40 million units. So, what does that mean?
There's 1.4 plus, is it extrapolation?
Is this extrapolation?
No.
Extrapolation kind of goes the other way, right? So it'd be us saying, well, I think this might be what it is. Really, really far out. We're actually doing this for a year that we know. Why is it negative?
Because the line can be negative. Like the line can keep going into negative values.
It can, but in this case, because we know the 2007 data value is 0.5, how could it possibly end up negative 1.40?
It's not actually linear, so it messes up the equation. So it doesn't.
Part of it is it's not linear, but what does this represent? It's a predicted value, and the line is dealing with all of the data together. So you draw this line, and it doesn't fit the data points perfectly. And so when you have the slope then puts it at a different data point value. Okay, and so let's interpret it. So here we go. The actual number of units sold in 2007 was 1.9 million higher than expected. So the expected value, negative or not, our actual value that we have is 1.9 million higher than expected. That's actually really good, right? I'd love for that to happen. Yeah, I was expecting to make 100,000 last year, but I actually made 1.9 million higher. It was a good year. So what are we going to do with this information? What we're actually going to do is now we're going to take this data that appears to be nonlinear and this linear model and compare what do our residuals look like. Okay? So here's what I'd like for you to do. I would like for you to fill in the chart. All right, so let's look at this for a minute. So we fill in our chart. And we notice that, we get all, so this is a linear function, right? So we plug in our year. We do our actual minus predicted, and then we plot our residuals. Here's why this is significant. So this is called a residual plot, because it's a plot of the residual, okay, like its name says. And what we're going to do with our residual plot is we're going to look for a pattern. The pattern is going to tell us what type of form our data takes. So let's look at this for example. For which points was the actual greater than the predicted? Which ones? First two and the last three. So if I do actual minus predicted, if the residual is positive, this means what? Summarize it for me. If the residual is positive, Actual greater than predicted. But if it's lower, so it's negative, the actual was less than predicted. In this context, what do you want to happen? Which do you want to be greater in this context? In selling iPhones. Yeah, you want your actual, you want to sell more than you thought you were going to. You'd love that. People get in trouble in this area with this sort of thing. And so, do you think the regression line is a good fit for the data? Why or why not? Explain using a residual plot. Here's how we're going to use residual plot. You ready? No. The linear regression is not a good fit. And this is the pattern that we're going to look for. All right? The residual plot looks curved. So the distribution is nonlinear. Okay, so the distribution is nonlinear. What we would call this is there is a positive, negative, positive pattern. So positive, negative, positive. And so what that kind of tells us is if you remember, if this is our plot, and I sketch in my least squared regression line, what that would mean is we've got data here, data here, data here. And so it would look more like a curve than a line. So what do you think is going to happen if we actually have linear data? What's our residual plot going to look like?
It's either all going to be above or all going to be below.
Is it gonna be at 0?
No,
No.
it's gonna be.
Me trying to figure it
Yeah, they'll be only on one side of it.
No.
Or it'll alternate like by 1 and 1, so that it still makes a line.
It won't have a pattern.
It's going to be random. If it's actually linear, okay, so if I actually have linear data, so if I come over here, and imagine, so here's my least squared regression line, right? And what we find is, you get some on, and you got some like this, right?
If it was perfectly linear, would it be all on?
So talk to me about residuals. So if residual is 0, what does residual 0 mean? There's no difference between actual and predicted, right? So if my residuals start to go like this and get closer to 0, what does that mean?
Value is closer to 1.
The R value is going to be closer to 1, right? So the tighter around 0 my residuals are, the better fit my data is. Does that make sense? Because residual measures like how far these are from the line, right? And so if I've got smaller lines, meaning the data is closer to the line, I'm going to have residual plot closer to 0. But to Annie's point, if I've got linear data, my residual is going to be random because I'm going to have some above, some below, but there's not going to be a definite pattern. Whereas if I've got some parabola here, right? Like if my data was in a parabola, I'd have residuals above, residuals below. Okay, I'd have like a definite pattern to my residuals. All right, I want you to hop over, skip the box for now. I want you to go to the check your understanding. So what you're going to do is you're going to do the same kind of thing. You're going to find a least squared regression line, and you're going to plot some residuals for the backpack weights. All right, so practice this skill here. Okay, so let's check this out. I left this one blank on purpose. So calculate the equation of the least squared regression line. So help me out. Somebody tell me. Let's do the formal version here. What do I start with? Y hat equals
16.24 plus 0.09x.
Okay. And what does it mean? Let's do the contextual version. Somebody besides Leon, how about the context version?
Backpack weight in pounds.
So backpack weight. And what does this hat deal mean?
Predicted.
Predicted backpack weight is equal to 16.24 plus 0.09 times, what's my explanatory variable? Body weight. Okay, so predicted backpack weight, 16.24 plus 0.09 times body weight. All right, so here's my residual plot. Yours looks similar. What do you think? What does the residual plot indicate about the appropriateness of the linear model? Can't tell if it's because you're on camera that you're shy or if it's
I
homecoming.
forgot.
What do you think?
It's appropriate because the data appears to be linear. The residuals don't appear to follow the pattern.
Are you allowed to comment on unusual features?
What? No.
Is that what it is?
Don't. No. I don't like that.
Because it will go back. Oh. No.
Okay. So we've got a negative, positive, negative.
Wait.
So you should say because this is negative, positive, negative.
It's really a stretch for a pattern.
That's so
Okay, let's talk about that in a minute. A linear model is not appropriate. Okay, so how random is random enough to be random enough to be random enough? I think that's the question, right? So how random does it have to be? Well, anytime you see a big gap, red flag. See the big gap right here? Okay, so that's an indication that we're going to have some sort of other patterning. I throw 1 or 2 points down here, we're random. We don't have a lot of data points. A lot of times with these, you're going to have a lot of data. We don't have that many data points, but if you see a big gap, red flag. Big gap should be a red flag. Okay, so negative, positive, negative on this. So make that slight change. This one's a little tricky because we don't have that much data and it looks sort of random. And then there's this one here, right? That's kind of mixed in.
That's unusual.
Okay, so that kind of throws you off. Maybe that's an unusual feature, but at the very least, see the big gap right there. Yeah, Gigi.
So my graph is like the complete opposite. So I think is the predicted what we solve for.
Wrap. So your
No, I
residual is
meant that,
actual
like-
minus predicted.
But the actual is that what was in the table?
The actual's in the table.
I thought we were solving for the actual.
No, so that's why this one's so important. So this is predicted. So these are predicted. Predicted weights. That's what the hat means. Okay, let's take a few notes in the box here and kind of sum it up. So here's our box. And let's talk about residuals in general and least square regression lines, etc. Okay. Okie doke. LSRL, least squared regression line. So it is the line with the smallest sum of residuals squared.
Wait, like that's a definition.
Yep. So kind of as I've been showing you, so check this out. If I've got, if I've got my least squared regression line here, this is what happens. I've been talking to you about this distance here. Well, basically what we do is we draw a square. We draw squares, and we square. That's what it means to have like least squares regression lines. You square the residuals. Why would we square the residuals?
So they're not positive, negative.
Yeah. So if I strictly just counted the distances, right? So let's say this one is 2 above, this one's 2 below. Well, all of a sudden I have 0 residual. Is that true? No, I don't have 0 residual. But together I have 4 residual. But I have to square them to take into account that there is a difference between the actual and the predicted. Okay, so the sum with the least residual square, which means if I draw this line here, well, notice now all of a sudden I have this huge residual here, big residual here, smaller here, big, okay? And so this line is the one with the smallest sum of the squares. I think kind of conceptually it would be easier to say it's closest to all of them. And so when we do our residual plot, so I've got my residual 0, positive, and negative. Here's a good one. No gaps. It's really good. It's random. So good has a random scatter. Here's a bad one. Okay.
So bad has a pattern.
What's that?
So bad has a pattern.
Bad has a pattern, like positive. So this would be a negative, positive, negative pattern. So this should be random scatter. Okay? All right, we have about 7 minutes left. I would like to spend a little bit of time talking about your homework.